How does Netflix guess your rating for a film you have never even watched? It fills the gaps in. And the move that does it is hiding inside every matrix, in every model you have ever used. Rotate, stretch, rotate. That is it. That is the whole trick, and it is the most useful factorization in machine learning. Last time, some direction survived a matrix untouched, its eigenvectors. But now try a pure rotation. Every single arrow turns. Not one stays on its line. A rotation has no real eigenvectors at all. The eigen trick just broke. And square matrices are the lucky ones. A non-square matrix cannot have eigenvectors even in principle. We need something that works for every matrix. Here is the fix. Forget eigenvectors. Instead, find two perpendicular input directions, call them V1 and V2. Push them through the matrix. They stretch and swing, but they land still perfectly perpendicular. That right angle surviving is the whole secret. Perpendicular in, perpendicular out. The input frame is called V, the output frame U, and the stretch factors are the singular values sigma. Let us read the formula right to left as a recipe on a unit circle. First, V-transpose. A pure rotation, it just turns the circle to line the special directions up with the axis. Then sigma, it stretches along the axis, sigma 1 across, sigma 2 up, and the circle becomes an ellipse. This is the only step that changes the shape. Finally, USA. Another pure rotation, turning the finished ellipse into place. Rotate, stretch, rotate, and any matrix at all is built. Any reshaping of a photo is the same three steps. Turn the picture. Scale it along the new axis. Turn it back. Rotate, stretch, rotate. That is every linear map there is. Look at the ellipse the circle became. Its long axis and its short axis are exactly the singular values, how far the matrix stretches in each direction, and they come out sorted biggest first. So the singular values are ranking. The first direction matters most, the last barely at all. The singular values are a top hits chart for directions. The first carries the most, the next a little less, and the tail carries almost nothing. Keep the hits, drop the filler, and you have barely lost a thing. Here is the punchline. Even a rectangle, a non-square matrix with different numbers of inputs and outputs, still splits into a rotation, a stretch, and a rotation. The blocks just change shape to fit. Eigenvectors work only sometimes. The SVD works always, for every matrix ever written. That is why it, not eigenvectors, is the workhorse of machine learning. Line the singular values up as a bar chart. Almost all the energy sits in the first few. The tail is nearly nothing. So keep only the top few directions and throw the rest away. The matrix barely changes, but you store a fraction of the numbers. That is compression. And this ranking is not a textbook curiosity. It is running inside the models you use every day. Let me show you 3 places. A ratings table. 4 viewers, 5 films, and a few gaps where nobody has watched yet. 20 numbers, but the singular values say only 2 directions matter here. So the whole table factors into just 2 skinny pieces, how much each viewer likes, each hidden taste, and how much each film has of it. 2 tastes, and they come out looking like action and romance, which nobody labeled. Multiply the 2 pieces back, and the empty cells fill themselves in. That is a recommendation. The Netflix prize was won on this idea, a factorization adapted to cope with all the missing entries. Take a giant table of which words appear in which documents. Raw, it is noise, words scattered with no structure. Now keep only the top few singular directions and throw the rest away. Words that mean the same thing collapse onto each other. Car and automobile land together without anyone ever defining a synonym. That is latent semantic analysis, the direct ancestor of every word embedding your models use today. Last one, and it is the deepest. Send a signal through 3 layers of a network. If the biggest singular value of each weight matrix is 1.4, the signal is multiplied by 1.4 every single layer. 3 layers and it has nearly tripled. 100 layers and it explodes. Make it 0.7 instead and the signal dies away to nothing. Exploding and vanishing gradients. Both are just the biggest singular value being on the wrong side of 1. So some models divide every weight matrix by its own biggest singular value, forcing it to 1. It is called spectral normalization. It is what keeps many image generators stable, and they find that singular value with the very same power iteration you saw last episode on every training step. One call gives you all three factors. Multiply them back and you recover A exactly. U and V are pure rotations. Their transpose is their inverse, and S is the ranking of directions. The full notebook is in the description. The map so far. Today, every matrix without exception is rotate, stretch, rotate, U, sigma, V transpose. You are here. What it buys you. Any matrix is rotate, stretch, rotate. The singular values rank the directions. And keeping just the top few is how AI compresses images, builds recommenders, and fine tunes with LoRA. Next, we cache it in, keep only the biggest singular values, and watch a photo compress and a giant model. Fine tune the same math, one small add on. Next, keep only the biggest singular values and you throw away almost nothing. The math that compresses a photo and fine tunes a giant model with LoRA. Thanks for watching and keep exploring. Next time, low rank approximation. How SVD compresses everything. Please like and subscribe ThirdEye Labs if you enjoyed this video and let me know in the comments.